we're going to tackle a huge question that really is the key to unlocking the future of computing. And this is the first step, the first question to many quantum journeys. What exactly is a qubit? Now, it sounds complicated, but its power actually comes from a surprisingly simple twist on the kind of information we all use every single day. Everything you're watching this on right now, your phone, your computer, it all runs on classical bits, and they're beautifully simple. A switch is either on or off, a 0 or a 1, but a quantum bit, a qubit, what can it be? Well, that's the central mystery we're going to unravel today, and to figure that out, we've got to start on familiar ground. As the quantum computing pioneer John Watrous said, the only way to really get a handle on quantum information is to first have a solid grasp on classical information. So let's start right there. Before we can jump into the strange new world of quantum, we really have to appreciate the world we're already in. We live in a world built on bits, the clear, predictable foundation of our entire digital lives. So let's start with, what is a bit? It's the smallest possible piece of information you can have. It can either be a 0, it could be a 1. That's it. There's no in between. Think of a light switch. On, off. It's super simple. Now, these are systems with clear, distinct, and classical states, but even in our normal classical world, we deal with uncertainty all the time. I mean, before a coin lands, you don't know the outcome for sure. So we talk about it in terms of probabilities. Maybe we have a weighted coin, so there's a 75% chance of it landing heads, we'll call that 0, and a 75% chance of it landing on tails, which we'll call 1. And we can actually capture this uncertainty with a neat little mathematical tool called a probability vector. All you have to do is list the probabilities of each state, so 3/4 for state 0 and 1/4 for state 1, and you just pop them into a column. This little vector neatly describes what we know about the system. Now hang on to this idea of a vector, because the quantum world is about to give it some serious superpowers. So we've got our classical foundation set. Now let's take the leap into the quantum world and meet the new star of the show. What is a qubit? It's basically a quantum version of a bit, but here's a mind-bending part. Instead of being an or like either a 0 or a 1, it can exist in a superposition of both states at the exact same time. It's a blend, a combination of both 0 and 1. Now, this is the secret sauce right here. The entire jump from classical probability to quantum power comes down to just two small changes to our vector rules. See, in this classical vector, the numbers are just probabilities. They have to add up to 1. But for a quantum state vector, the numbers can be complex numbers. This adds a whole new dimension called phase, which is what lets qubits interact and interfere with each other. And it's not the numbers itself, but the sum of the absolute squares of those numbers that has to equal to 1. And this right here is the crucial point, those two tiny mathematical tweaks. That's everything. That's the source of all the incredible potential of quantum computation. It's not some physical trick. It's a fundamental expansion of what some information can be, all written in the language of math. Now, I know this idea of superposition can be kind of hard to wrap your head around, but luckily physicists have this beautiful tool to help us visualize it. Meet the Bloch sphere. Think of it as a map of every possible state in a single qubit that can, in all, be plotted onto a surface of a sphere. This turns all that abstract math into something we can actually picture. So let's build this mental model together. Picture the Bloch sphere like a globe, the point at the very top, the North Pole, that represents the definite classical state of 0. That's our off switch. And if the North Pole is 0, you can probably guess what the South Pole is, right? The definite classical state of 1. So far, this looks like our classical bit with its two options, but here's the quantum leap. Every single other point on the entire surface of the sphere, there is an infinite number of them, and it's a valid state for a qubit. Each point is a unique superposition, a specific blend of 0 and 1. So a qubit doesn't just have two states, it has an access to a continuous infinity of possibilities. So we have this object with literally infinite states. How in the world do we actually compute with it? How do we get an answer out? We do it through a process called measurement, and this is where the weird quantum world has to connect with our classical reality. When you measure a qubit, you essentially force it to abandon the superposition. It has to choose a classical state, collapsing into either a definite 0 or a definite 1. So let's go back to our Bloch sphere. A qubit might be in a state somewhere near the equator, let's say a perfect 50-50 mix, but the instant we measure it, its state vector snaps. It goes straight to either the North Pole, giving us a 0, or down to the South Pole, giving us a 1. All of that infinite possibility resolves into a single classical answer. So if a measurement is how we read the result, quantum gates are how we do the work. A quantum gate is just an operation on a qubit. These operations are called unitary, which is a fancy math way of saying they're reversible. You can always undo them. And visually on a Bloch sphere, you can just think of these gates as precise, smooth rotations that move the qubit state from one point to another. So let's put all these pieces together. We have qubits and we have gates. How do we combine them to actually perform a computation? Well, we use something called a quantum circuit model, and honestly, it's a pretty direct parallel to the classical circuits in your computer. In a classical circuit, you have wires that carry bits, and gates that perform logical operations like and, or, and not. In a quantum circuit, the wires carry qubits, and the gates perform these unitary rotations, and at the very end, the measurements. And learning to read one is pretty straightforward. Each horizontal line, that's just the life of a single qubit. As you move from left to right, you see the operations, the little boxes, which are the quantum gates, that are all applied to it one after another. Then at the very end, that little symbol usually means a qubit is measured to get a classical result. This whole model of computation built on these qubits, it opens the door to a phenomena that just has no classical equivalent. Things like entanglement, where the fates of multiple qubits can become linked in ways that totally defy our everyday intuition. So let's bring it all home. We've gone from a classical bit, which holds one of two values, to a single qubit, a single unit that contains an entire spectrum of infinite possibilities. And that leaves us with one final, really profound question. If just a single qubit holds that much potential, what extraordinary problems could finally be solved by harnessing millions of them? Thank you for listening and tuning into this episode of QuantLock. Keep questioning the quantum world.